All right, everybody. So let's get started. So the first thing I wanted to show was the grades. You did very well in your first homework. Those are the proportions of each score. More than a third got a 10, so good job. I know it was hard, but I think hopefully it was worth it. The homeworks are going to get progressively less step by step and more free form. So I know that's not hard, but that's how data science is. And for your final project, there will be no step by step. So we'll try to keep it as objective as possible in that context, but just so you're prepared. And so we'll try our best to be fair when we grade. So when it is open-ended, and there'll be more than one possible answer. So don't get too stressed up about that. All right. So I think you, just judging by what I saw, you guys are doing well. I saw there was a lot of questions, sometimes angry questions, but that's good, just because I think you all are learning. Okay. So another less positive finding, and this was just not obviously not the majority, but we have some cases where there was a cut and pasting of answers. So just to remind you of the policy, you can work together and discuss the homeworks, but the code, you have to write it yourself. And we are going to detect most cases where you cut and paste, even if you change the name of variables, because we have ways of doing that. And that is not acceptable. We have some cases, we're investigating them carefully, and we'll proceed as the university tells us we should, but just I want to be very clear, you have to write your own code. And if you do, the chances of it matching somebody else's is almost zero. So just remember that, please, for going forward. Anything else to add, Marina? Okay, homework are due Thursday. It's just, yeah, okay. You know that. All right, so a little bit more about what's coming and what to expect. Ooh, yeah. So the next topic, we're gonna continue with the polls and the homeworks. We might have one more lecture just discussing some of the deeper points of how to predict the outcome of the midterm. But we're going to move on next week to what some call machine learning or statistical learning or a prediction. And we're going to have a couple of interesting problem sets there too. So that's coming soon. And the first part, we're going to use sports again to predict, to try to do what the Oakland A's did. We're going to try to figure that out and see if we can come up with our own ways of choosing players. And that's becoming more of a prediction problem. So that's what's coming. The other thing I wanted to point out is that one thing we learned from just this first week and this first homework is that there's a lot of variability among the students' knowledge of statistics and computing and all that, where we have a specific level in mind in which we're following the class. So some of you will think it's too hard. Some of you will think it's too easy. That's not going to change. But we are trying our best to have the homeworks have parts that are more advanced and parts that are... but the general homework is meant so that anybody who's in the class can, if they work hard enough, they can complete it. So one thing you can do if you think it's too easy is you can try to answer the questions. We pose a general question. You can try answering that question without looking at what's coming next, at the hints we give you. You can try that, and then you can see, and then you can compare to what we think you should do. So that actually will be a very good learning experience, I think, if you do it that way. It's one recommendation. In class, when we're talking about basic stats, you can, let's look at daydream or whatever it is you want to do. And then hopefully in the class at some point we'll get to the point where we connect statistics to the problems. And that part, I think it doesn't matter how advanced you are statistically or computationally, it's still going to be an interesting discussion, I hope. Okay. So now we're going to start with some basics. With that said, we're going to go back to some basic statistics so that we can do what Nate Silver and others do, because they do use all this in their poll predictions. And today we're going to start with we're going to go over basic stats, but maybe within 20 minutes we're going to get back to seeing how this is used in novel ways in these polling problems, aggregates problems. Okay. Okay. So all the stuff that we're going to talk about today, we have been hinting at throughout the lectures, and we've been making simulations, and we've seen some of this, but we really haven't talked about the specifics of the mathematics behind it. And now we're going to do that. I think this is a better way of doing it, because now you've actually done all this and you understand for real what these things mean, because if you have been doing the homework, you have already encountered some of these concepts without necessarily knowing how statisticians call it or how they think about it mathematically. So the first one, a very important one that we have been hinting at, is this idea of variance, standard deviation. So we already did that a few times. And there's the official definition of the variance or the standard deviation, which is just the square root of the variance. So it's basically an average distance to the mean of a list of numbers. It's easy, right? So that's the formula. And in Python, there's a way to write it, and you just get that. Okay, so here mu is the average, and I'm using mu and sigma, Greek letters, because these are fixed quantities of that list. There's no random anything just yet. It's all just a list of numbers, and you can get this. In more advanced statistics, you would then turn those lists of numbers into a continuum, and you can still define these things. But ultimately, in practice, it's always discrete. We just use the continuous approaches to approximate what happens in the real world in a more mathematically convenient way. Okay, so one thing that will help you when you're analyzing data and talking about data is to talk when you're talking about variability is try to always report and think of the standard deviation, because it's in the units that you care about. So when we talk about height, saying that the variance is 9 inches squared is weird, right? What is that? That's not height, right? That's something else. So it's better to talk about 3 inches standard deviation. That's clear. You know, the 3 inches is how much a range of about 12 inches is where most people are. Okay. Now another thing we talked about is that when x is normal, when that list of numbers has distribution is normal, then mu and sigma is everything you have to know to describe anything about that list. What proportion of that list is in any given interval? Okay, now random variables. How does this all connect to the variance and all the stuff we're talking about? So this is the polls. In the poll, we have a random variable x, and it has a probability p of being 1. So what is x here? In a poll, what is it? 1x would be what? Not a trick question. Don't be afraid to just say it's obvious. So what is x in a poll? Okay, it's yes or no, but what does it represent? A person, a vote. Okay, that's x. So you grab a person at random and you ask them, are you a 1 or a 0? It's the probability of being 1 is p because you grabbed it at random. Now, what's the variance of x? So that's kind of a weird thing to ask because it's just one number. But it's a random variable. If we keep doing it and doing it and doing it, it's going to have a variance. So in this particular case, we can use that formula we just showed to compute the variance. Right? So there's sigma is going to be 1 minus p. There's an error. Oh, no, that's it. So 0 minus p squared. That's the formula. What proportion of people have a 0? 1 minus p. what proportion of people have 1, P, and you get that formula. So that's the variance for just one person, and it has that shape there. P is the proportion of, in this case, we can think of Democrats and or people voting for Obama in the example we've given, and then this little shape tells you where the variance, how much variance it is. So just to give you an intuition of why that looks like way, think of the case where you have a probability 1 of being a Democrat. So if you go to DC and do a poll there, that's basically a probability of 1 of being Democrat. Is that the highest? I think it is. So if your variance of those numbers, zeros and ones, is practically 0 because they're all 1s. There's no variance. If you go to somewhere like Ohio, then it's about 50/50, and the variance is bigger. You're going to have some 1s and some zeros, so you have more variance. Okay. Now the average. So we take a poll. So we ask n people, and then we take the average of these zeros and ones. And now I'm going to ask you in this context, so we take the average, which I'm going to call x bar. So now I have n x's. They're all random. They're 0, 1. I take the average. That's just the proportion of ones. And now I'm asking you, what is x bar and what is p? So what's x bar? What? Of what? For the percentage from? No. X bar is not the people who voted yes. X bar is a proportion of people voting 1 in poll. In the poll. So that's a random variable because we picked a random sample. So you're doing that in your homework. In your homework, you're grabbing random samples and computing x bar. And if you do it over and over again, you get different x bars. Now what's p? That, or somebody already answered that when I asked what x bar was. What's p in our polls examples? Nobody? Oh, in the previous question, it was 0.53. In general, it's what? Voting 1, Democrat. Okay, on election day, or is one way to think about it. So the P is election day results. X bar is poll result. So which of these is random? X bar is definitely random because we took a poll. How about P? So okay, so P, people are saying it's not random. No, it's not random because you can think of it like the day of election, everybody knows what they're going to do, and that number's fixed, and we're going to find out soon enough. Now, so P is not random in this context. Now, when you look at the 538 and all these websites, other websites, they tell you the probability that the Democrats are going to win the Senate, or the probability that Obama's going to win the election is, and they give you some number. So that is P. They're talking about the probability of P being something or other. So what's that then? Where does that come from? So that's something to think about when we interpret all these aggregators. That is something that is not the standard way that people do polls. That's something new, and we're going to learn a little bit about that. Okay, so just think that, what does that mean that P is now it's a random variable if we're talking about its probability. So that's not, we haven't covered that yet. That would be more like a Bayesian analysis, but not quite. But that's different than when we do it this way. Okay. We're almost done with this. Okay, so the sample average. So this is something we hinted at last time. So now we're going to introduce some statistical terms. It's E, which we're going to see again. You use the E in machine learning? Okay. So E stands for expected value. It's yet another name for the mean and average. And in this case, it's the average of the random variable. So if we saw this random variable 1 trillion times, what would be the average of that random variable? And here we know it's p, right? Because that's the population it comes from. So on average, p percent of the time, xi will be a 1. So that's the expected value or the mean of xi. So that's, and you can compute it very easily there, and that's what you get. So each one has an I. So now for the average, we can make this calculation, and this is a little rule that you will use often if you become a data scientist, that the mean of the sum, if you sum random variables, and you want to know the mean of that sum, it's the sum of the means. So you know the mean of 1x. If you want to know the mean of the sum, you take the sum of the means. So that's why we're summing up the p's, because the sum of the zeros and ones, that's their mean. And then we divide by n. That's another little rule you use. Scale changes are preserved. If I have a random variable, I multiply it by a, the expectation is also multiplied by a. That's very intuitive. Right? If I have something and I expect it to be p, if I multiply it by a, then the expectation multiplies as well. So we use this. We're going to use this because what that tells us is that on average, our pole will have the true p. That's an important characteristic here, and the one that Nate Silver et al. Use very, very often. All right, now the trickier one, the variance. So we already computed the variance for one of these 0, 1s was p times 1 minus p. And now we have another rule for the variance. If you have these variables are independent, that's very important to remember. If they're independent, then the variance of the sum is the sum of the variances. So if I sum a bunch of xi's, if I take a pole and I sum a bunch of xi's, I get to sum their variances. So there I'm summing their variances here. And the other important rule is that scales are squared. So if I multiply by 1 over n to get the mean from the sum, then I get an n squared outside, 1 over n squared. So this is the variance of the average of these zeros and ones. Okay, so that gets us to the utility of these poles. Why do they work? So x bar, we just showed, has mean p, and this is something you're doing in your homework. Through simulations, you're getting at this. This is the theory that tells you what you should get, but you're doing it through simulations. You're creating x bars, and you're noticing certain characteristics of that distribution of x bar. It has mean, the true p, and standard deviation, p times 1 minus p, which is going to be roughly fixed because most p's are around 0.5. And then you have, so it's going to be about a quarter. About a quarter. And then you have divided by n, square root of n. So that's, now we call it the standard error, as we mentioned last time, when it's a random variable. The standard deviation of the distribution is called the standard error. It's just a jargon that we're going to use over and over again. Okay, so what does that say? X bar, when you take a ginormous poll with 10,000 people, then the standard error is going to be square root of something divided by 10,000, so that is now getting to be a small number. You make that bigger and bigger, that value gets smaller, smaller, smaller. It varies less, less, less. And then that means that if you get n, you make n infinity, then x bar becomes p. That's called the law of large numbers. And it's also called the law of averages, I think. And you often hear it misused by sportscasters and others when they say a player's due. I don't know if you've ever heard that before. So when someone's, or in roulette, red comes out 10 times in a row, people say, oh, green is due. No, not green, black. Green's never due. Black is due because there's been 10 reds, and on average, it has to be half and half, because that says so. Okay, that's a misuse of the law of large numbers because the events are independent. But that's the law of large numbers tells us that on average, that roulette is going to come out half the time red, half the time black. and then a little bit less because of green. Okay, so that's the law of large numbers, and poles are using that to get close to the real p. They want to get close to the real p, so they get n to be bigger and bigger and bigger. The bigger it is, the closer they should get to p. All right, so that's the implication. So now I'm going to ask you, what is the standard error of a pole with a sample size 1,000? So p is going to be about a half. So what is the standard error? You can use your computers to tell me. You can use that formula up there. You're doing it in your head? What is it? No. So what is it? Huh? P is, about a half. It won't change it too much. 0.02. Okay, have you seen that before? If you look at newspapers and you look at the polls, they almost always say plus or minus, and then 2%, 4%, it varies. That's what they're telling you. That's where it comes from. So if it's 1,000, that's what you should get. All right, this is all theory. So what did he do? He put 0.5 times 0.5 divided by 1,000 square root, and he gets 0.02. Okay, so here is the distribution that you guys are supposed to do in your homework. Something like this. This is a pole with 100. Right, so you can see the point. I think I made p equals to 0.48 in this case. And there's the distribution. It looks normal. We already showed that last time. If I increase n, what happens? The standard error gets smaller and smaller and smaller and smaller until you just get there. All right, so that's what happens. To the standard error. Okay, now so the central limit theorem is what we used last time, and it tells us that the average of independent outcomes is normally distributed. So that makes it even better, because that makes it even more useful if this happens, because before we were saying if the pole is large, if the number of people in the pole is large, we're going to be close to the real number, to the real proportion. This is giving us much more information, because it really tells us how close we are. So once we know that x bar follows a normal distribution, we know its mean, we know its variance, so we can compute an interval that has 95% probability of being on top of p. That's how we construct that's what we use to construct these confidence intervals. And there I just made 50 of them. I just made them 50 times. How did I make 50? Because I took 50 poles, and you can see them moving around because they're random. But about 95% of the time, they fall on the truth, which I think is 0.48. So that's called the central limit theorem. We also use it very often, that the averages, sample averages, and there's a lot of things in data science that can be considered to be like an average, so have this property. And we can use it to give probabilities, confidence intervals, etc. And the Nate Silver et al., they use this. They don't bother with the binomial. They know these poles are big enough, and they go straight to this. They just try to get at that denominator. And that's where it's going to get tricky. That denominator, the theory doesn't work. The theory I just talked about, it doesn't really work very well. Well, it does work. It just doesn't work as well as other things you can do. Okay, so that's fake data, right? I made that. And that's part of what you have to do for your homework. Oh, yeah, I forgot to mention, these slides will be up on the web with the code soon, hopefully tonight. So you have these random poles. So now that was on a computer. Now let's go to the real world where the same thing was done. Not on a computer, much more complicated procedure than typing IPython code. You call people, you write down the number, you take the average, and all that work is reduced to a little stupid plot in a stupid little class. Millions and millions of dollars worth of poll data. It's summarized up there. So what I have there is the same. So I want you to realize is this the same. It's almost the same thing as what you did on your computer. This is the real thing. You take a random sample, just like on the computer. You get zeros and ones. You average them, and then you use this theory to make little intervals. 95% confidence intervals. Okay? So one of the first things you notice when you look at that plot, I have put them in order. I have put the, this is, let me just back up a little bit. This is the last month, or is it the last week? It's the last week, or the last month. I think this is the last week before 2008 election. And I have the, I've put the polls together by the pollster. So there's different companies that do this, and I've put them together in colors. So you can see ABC, then something else. You can see, what else can I read? Fox, Rasmussen, Sogby. So when you look at that, these are all supposed to be polls. So one of the things you see is that the bars go up and down. That's because they have different sizes. But there's something in this picture that tells you that all this theory we'll be talking about is not quite right. What is it? Are the little bars about 95% of the time on top of the truth? That's the truth. That was election day. And I think now I'm showing you an Obama percentage in 2008. So look at that picture for a little bit and tell me why all this theory isn't quite right. Ooh. Oh, what did I just do? Go ahead. Make it a little bigger for you guys. Say that again? Too many bars not intersecting the truth. Yeah, so I think there's a little bit less than there should be. If you count, it's not that far, but it is I think it's less than 95. Yes, that's the bigger problem. Everybody see what he's just pointed out? Look at Rasmussen. They really failed, but they failed consistently, which is bad. It's bad to be consistently bad. If you look instead at, there's other polls that had bigger bars, but they were on top more often. Right? So Rasmussen was more consistent than, for example, the Diageo hotline, which might be an Interpol. That's kind of vary more, but at least they had their things wide enough and it's falling on top. So that is the bigger problem here. You can also see that Pew was twice too high. There's one up there, I think it's CBS, that tends to be high on they tend to be consistently high. So the way to say this is that these are not independent. That's one way to say it. Right? The pollsters have an effect other than just this randomness that comes from taking a random sample. Nate Silver calls this the house effect because I guess he's a gambler, and he's calling it a house, like the house is where you go. The house is what in gambling you call the casino that takes your money. So there's a house effect. So each poster has an effect, and if you see that, then that means that the theory we've just shown about polling isn't quite right. There's something else going on here. It's not clear why this happens, although there's some theories of why it happens having to do with how they ask the question, and they might have the group they ask wrong, and then they stick to that technology. Like they might have different techniques for determining who's a likely voter that maybe biases them in one way or the other. Okay, so now let's talk about what these aggregators do instead. So those bars that I put up there, they come from statistical theory that tells us if you take a random sample, you can make a confidence interval, and you get what you get. Now, the pollster aggregators take a slightly different approach, And they treat those points as the data. So the data isn't, the raw data here are the people that as asked. So the data is a bunch of zeros and ones. That's the data. But they ignore that, and instead, they don't completely ignore it, but they, in a way they ignore it, and instead treat those points as the random variables that we work with. That's kind of the, I would say that was a big intuition, the big contribution of this approach to view it that way. It's kind of a nice idea. It is a nice idea. It's a pretty smart idea. Okay, so you kind of forget how these polls were done. You just say, oh, there's a bunch of data that relates to the truth that I'm after. Now we're going to figure out how they relate to the truth we're after. Okay, so everybody's with me now? We have now, instead of thinking we have 1,000 zeros and ones, instead we have 105 poles. And each one of them is a random variable, so I can start doing statistics and data science on this. So there's the histogram. What do we do first when we have data? We make a histogram. Look at the histogram there. There's the poles. Here's a QQ plot. Looks pretty good. Good. It looks like normal. Maybe it's a little bit, if you look closely, it has a little bit of a C shape. But that's not that easy to see. So, yeah. Oh. What do I do to check the sound? This thing?
It seems that your laptop microphone is activated and not the...
Oh, so I don't know how to check that.
On the Mac, I don't know either. The adapter.
The sound quality is very poor for the students who are watching.
Okay, so I'll stay here. Okay? All right. So yeah. So now we're starting afresh with a new random variable x. It's 105 observations, and now we can ask ourselves, what's the distribution of x? Well, it looks normal. We might use that. We might not. So now everything changes a little bit. So what's the variance of one of these random variables? Okay, so we can go back to the first slide and just figure it out, and we get an answer. We say, well, it's a poll. We average. The theory says this, but now we're not going to use that for now, and instead we're going to say this is just a new set of variables, and we want to describe it. So what is the variance of this new sample? And we're very simplistic here. We're not taking into account poster effects or sample size, but we're just assuming we just got this data and we want to do something with it. So now we have a new set of data, and now the question is, what's the variance of this data? And we don't want to use the theory. We want to use the data instead. See that distinction? So we can use the same formula to estimate the variance from the data itself. So there's a formula for doing that. We divide by n-1 for technical reasons that really it's not worth, I don't think, discussing. N is 108, 107, 108. Won't make a big difference here. But if I don't show that, I'll get some nerd rage from statisticians if I just have 1 over n. So we basically take a standard deviation of the observed data. That's called the sample standard, the sample variance. The square root is the sample standard deviation. And that is the new variance that we're going to estimate. So now we're going to take an average of those polls. So we have 108 numbers, and we take an average of those polls. So what is it? Does the central limit apply to this? This isn't binary data, so the binomial thing doesn't work anymore. It's just data that we found on the internet. So does the central limit theorem apply here? Can we say x bar is also normal? Any thoughts? Yes, why? Okay, yeah, so the central limit theorem says that you take a random sample of something, and they're independent, you take an average, it's normal. That's what the central limit theorem says, and in that case, then this x bar should be normal. Now, what would be a counter argument to that? Why it wouldn't be that? One counter argument would be it's not independent, right? There's these poles effects. Another argument could be they're not really the same random variables. There's different poles, different sample sizes, etc. But let's keep going as if that's right. So then what we do is we say x bar is normal. And we can now we're going to use this. We're going to use a model that says that the expected value is the true p. Each one of these x bars are unbiased. And then the variance now is the variance we computed from the estimate of the variance is the variance we computed from the data divided by the nu n, which is 108. Okay, so now we have the mean is 0.5256. That's just what we get. And the standard deviation is 0.063. So one of the things we can do now, if we're really going to test the original theories, we could compare that standard deviation to what you expect to have for one of these individual x's. Right? Each one of these individual x's, the theory we talked about earlier, gives us a standard error. So you said for a pole with 1,000, it was like 0.02. For a pole with 2,000, it's so much. So now we're getting another number. And that number just comes from the data. So, but the most powerful thing of all this is that look at the standard error now. It's now 0.00159, and our 95% confidence interval, instead of being from like 49 to 53, is very small. Why is it so much smaller than our previous ones? So remember these guys? Those all are about 4 percentages wide, and now we're at less than 1%, 0.1% wide. So how come we're so? And by the way, I think the correct answer was 52 point something, 0.7. I think it's in there. It's in the confidence interval. It's a very small confidence interval. It contains the truth. So why is it so much smaller? How did all of a sudden did we get such a better confidence interval? Where does this power come from? So the sample size is only 108. But it used to be 1,000, 2,000 before. Nice, but they're close, but you have to be more precise. Yeah. We used the normal approximation before too. The normal approximation doesn't make you more precise, it just makes it easier to compute stuff. So one pole had 2,000. Now we have only 108 data points. But there's something that has a much smaller variance here than there. So that when you do the homework and you program it, I'm hoping you'll get a better sense for why this is. But the reason is that in the first example, our data point, the variance of a data point was was 1 or 0, and the variance was p times 1 minus p. Now the variance is a pole. So the variance of one point now is 0.01. So we went from the square root of 0.25, which is 0.5. We went from 0.5 to 0.01. In a pole, the unit is a person. In the average of poles, a unit is a pole. The pole average has much smaller variance than the individual person. A pole is a much better predictor of the election than one person. That's another way to think about it. So that's where the power of this comes from. And at the end of the class, we'll come back and discuss a little bit more about this some of the approaches that the pollsters use to improve this model. Because like I said before, it's not quite right to do this because these X's are different. They're correlated. They're not independent. They come from different pollsters that have different properties. And you can use all that to make this even better than what we just did. All right. So now that was only looking at the last little bit of data, the last week. What happens if we now want to use even more data? Let's go and use all the data we have available to us. And what if we were doing this as we are right now? Right now we're what? We're about here, I think, right now. How many days to the election? About a month and a bit, maybe here. So the election's in a month and a little more. So we're here. Imagine we were here in 2008 and we had to predict the final outcome. So now in your minds, erase everything to the right. And imagine you had to predict what was going to happen towards the end. So the first thing you notice when you look at this picture, can everybody see that there appears to be a strong time effect? So here is now the weeks stratified. So every box plot